Good afternoon, everybody. I am Kasi Rigo from the Institute of INAF, Institute of Radio Astronomy in Bologna, Italy, and from the Italian ALMA Regional Center. I would like to welcome everybody to today's talk, which is given as a part of the ALMA Recounts of Cosmic Conundrums series, organized by the European Arc Network. The European Arc Network consists of 7 nodes distributed throughout Europe and coordinated by ESO. The main goal of the European Arc Network is to maximize ALMA's scientific return for the European users. This includes providing virtual or real-life face-to-face user support to anybody who wants to use or get to know more about ALMA, but also anyone who needs support with the proposal preparation, the data calibration, data analysis, archival science, and much more. It also includes, though, the organization of talks like today's to celebrate and promote ALMA science in Europe and to stimulate interactions between astronomers. In every talk of the ALMA Cosmic Recounts of Cosmic Conundrums series, a major astronomical question is discussed. The speaker describes the context of the question and then focuses on the ALMA contribution to the field, the past and the future. The aim of the series is to highlight the unparalleled contribution of ALMA to the broader astronomical landscape and to provide an outlook towards the future. So today we are delighted to have with us Davide Fedele from INAF, Osservatorio Astrofisico di Arcetri, Florence, Italy, and also Torino, who will address the question, how and when does planet formation happen in disks? Davide is an expert of protoplanetary disks around low-mass stars and planet formation. For his studies, he has used numerous ALMA observations, but also data from other instruments, such as the Herschel Space Observatory and the VLTI. The talk will last about 45 minutes, after which there's time for questions. Please feel free to put in your question in the YouTube chat at any time, but just know that the questions will be most likely answered after the talk. And with that, I give the floor to Davide with his talk about how and when does planet formation happen in disks.
Great, thank you, Kasi. Let me share my presentation, slideshow, playing for start. Okay. So thanks again, Kasi. I would like first to thank the organizer for this invitation to talk today about ALMA, the ALMA view of planet formation. I should say that the question how and when planet formation happen in this is very quite a big question. So I tried to collect the major highlights, and I hope to answer this question by the end of the talk. So why we are interested in studying planet formation? I think you know quite well that as of today, we know more than 5,000 exoplanets, 5,000 confirmed exoplanets. And when we look at them, when we look at the properties of the planetary systems, we see a lot of heterogeneity. In this plot that you see here, we see the planets in the period mass plane of the parameter space. And we see that essentially planets, the exoplanets, cover a very wide area. So the challenge for any planet formation theory today is not just to explain how planet formation happen, but also to make sense of this heterogeneity between planetary systems. So historically, the two main scenarios, the two main theories to explain, to form planets, in particular giant planets, are the so-called co-accretion model or the gravitational instability. The co-accretion is the standard model for planet formation based on mainly on the solar system properties. Gravitational instability historically is the first theory proposed, and this is also very much useful to explain some of the properties of exoplanets. Very quickly, the core accretion scenario is a multi-step process. It starts from is a bottom-up approach, if you want. So it starts from the grain growth of dust particles via coagulation, then the formation of larger bodies via collisions, formation of planetesimals, which are kilometer-sized bodies, and then the formation of the core of protoplanets, planets, and finally the gas accretion phase. Now, so if we look, what does it mean? We need to increase the dust particle size by 14 order of magnitude inside the disk, and this also has to be done in a very timely fashion, because between in an age between 3 and 5 million years, most of the material has disappeared. Now, in this process, there are two main barriers. The first barrier is the radial drift. Essentially, when particles start to grow in size, at some point they feel a headwind by the gas, which rotates in a subcarrier velocity, and the particles start to drift inward. On the other hand, when assuming that you are able to form millimeter and centimeter sized particles, when you try to produce even larger bodies by collisions, what you realize that the collisions at some point lead to either bouncing or fragmentation, and these are two main barriers of the core accretion theory. There are ways to overcome these barriers. There are different ways, actually. One scenario proposed many decades ago to explain the rapid formation of Jupiter is the snow line. Essentially, inside the disk, when you move away from the star, the temperature goes down, and essentially the temperature reached the condensation temperature of some of the major species, like water, CO2, and CO. As these molecules start to condense on ice on top of dust grains, there's a steep, rapid increase of the solid particles, of the solid surface density, and this may facilitate the formation of planetesimals. This now also today is also applied to other systems. There are again other theories to evolve dust grains to form planetesimals. One of them is the streaming instability of the Peeble accretion. Essentially, let me reopen the movie again. Okay, let's start again. So the idea is here that particles are locally concentrated along the Keplerian flow direction, and this can lead to the formation of kilometer-sized bodies. And this, with the help of Peeble accretion, is capable to form the core of giant planets. So theoretically, all of this is possible. Gravitational instability, on the other hand, what it happens is that when a disk is gravitationally unstable, the GI, the gravitational instability, produces spiral waves. The disk fragments into dense clumps, and these clumps can become self-gravitating seed of gas giant planets. And now, while core accretion is a slow process, the GI, gravitational instability, is able to form giant planets on very short time scale. What are the conditions for gravitational instability in disks? We can look at this at the tumor parameter Q. When Q is less than 1, a region of the disk or the entire disk can be gravitationally unstable. Now, without going too much into the details, the Q is proportional to the sound speed, to the rotational velocity, and to the inverse of the surface density. This means that GI is efficient in cold, the cold outer region of massive disks. Now, thanks to ALMA and many other instruments in the last decades, we learned quite a lot about the internal structure of disks. And this is a schematic view taken by the recent review, PP7 review by me, Otello, and collaborators. What I just want you to take from this figure is that when we look at the submillimeter, when we look at the disk at submillimeter wavelengths, we are looking at the internal structure of the disk at close to the midplane or the midplane itself. When we look at the disk at scattered light at near infrared wavelengths, we instead look at the top layers of the disk. So before ALMA, there were intensive observational campaigns to derive the surface density profile of disks, and this was more or less the situation before ALMA. Essentially, all disks appeared to have very smooth surface density structure. In some cases, some object there was hint of an inner cavity, but very large cavity. Otherwise, the disks appeared again very smooth structures. What you see here is the comparison of the expected surface density profile of the minimum mass solar nebula, the nebula, essentially the protoplanetary disk that gave rise to the solar system. And on the other side, you see the status of the art of the surface density profile in disks, taken with the SMA before ALMA. Why ALMA is so important in studying disks? Well, for two main reasons. The first is the resolution, the angular resolution, which translated to linear scale at the closest subforming region of torus, allow us to observe disk substructures at the resolution of few astronomical units. On the other hand, is the sensitivity of microjansky in the continuum and a few millijansky in the line, RMS. This is very much important because allow us to detect very faint emission, in particular for the gas. This means we can now study the molecular isotopologues, the rare isotopologues, or even the large molecules and the complex species. So now you know this object very well. This is HL tau, and this was really the best, highest resolution image that was possible to obtain. If I remember correctly, this is taken with Karma array by Kwon. A few years later, the same disk observed with ALMA appeared to be completely different. Now, while before we had a smooth structure with not really obvious evidence of ongoing planet formation, now ALMA revealed this very peculiar structure where the dust is focused on in concentric rings separated by gaps. What I mean by gap is a region of low dust surface density. Now it's hard time to try to summarize all the high angular resolution campaigns because there were really many in these years, but schematically, what we learned from ALMA in the last decade or so is that disk appears in four main classes. We see disks with narrow with rings and narrow gaps. Other disks have wider gaps and sometimes an inner cavity, an inner dust cavity. All of this is dust continuum. Sometimes we see azimuthal asymmetries like arc or shoe-shaped structure. In a few cases, even spirals. This is another gallery of ALMA images by the recent review by Sean Andrews. Now, okay, let's have a look at the rings and gaps and cavities, which are by far the most common structure that we see with ALMA disks. There are different ways to form rings in the dust surface density. The first one that comes to mind is the planet dynamical clearing, the interaction of the disk essentially with an embedded planet. Is it possible also to form a ring with essentially is a byproduct of the MRI instability through the zonal flow at the edge of a dead zone. Also the condensation fronts, the snow lines was shown before. Also the snow lines are able, in principle, able to pile up dust particles and concentric rings. Photo evaporation can also form cavities. MHD winds seems to be very efficient in, especially in the very early phases of disk evolution, to form rings. And there are many more theories. All of this is very good because, as I said before, we have a problem in growing theoretically in growing the dust size, the dust particles because of the radial drift. Now the fact that forming rings is so apparently so easy, this is a good news for us because it means that dust can easily be easily trapped in these rings, slowing down the radial drift. I think that I find that one of the very important result came from the D-sharp survey, the survey of disk at high angle resolution. Are the properties of the dust in the narrow rings. Essentially, the dust in these rings appear to have always the same or very similar optical depth, and this is already a quite remarkable result. And now Stamler et al. Interpreted this result in terms of planetesimal formation. Essentially, we see that the dust in rings has grown in size. So okay, we have millimeter-sized particles, but the fact that the optical depth doesn't increase a lot, it's always below unity. This might imply that larger particles, centimeter and larger particles, are actually incorporated in planetesimals. So this is quite. So if you remember the core accretion story, this goes very well with the core accretion scenario. Also very impressive, I think, is this object here. I will talk about this object later on, but this is the same disk observed at just different angle resolution. You see that the dust itself is focused on two main rings. But the outer ring, when it's observed at high angle resolution, in this nice work by Sebastian Perez and also by Enrique Macias, you see that the outer ring at nearly 70 AU is actually fragmented. So it looks that this is also, okay, a planet can also do this. But this is also in very good agreement with the formation of planetesimal in this outer ring. Okay, now among all the possible scenarios to form dust rings and gaps and cavities, we are quite confident that in some cases, especially in the case of inner cavity or wide gaps, we are quite confident that these are evidence of giant of disk and planet interaction. There are three main ways to identify planetary disk interaction. The first is, of course, the direct detection, and I will talk a little bit about this in the next slide. Is the famous case of PDS 70, and this is a direct detection. So you actually you see the planet emission. But this is also very tough and very challenging because the planet itself is small, and the emission intensity is also weak. There are indirect ways to see the presence of a planet, and one is through essentially is through the perturbations of the planet to the gas surface density or to the perturbation of the dynamics. Okay, let's see how a protoplanet look like in a direct imaging observation. On the left side, you see the detection of two protoplanets inside the dust cavity of PDS 70. Now, these observations are essentially comes from near infrared observation. This is from VLT sphere, but notably. ALMA allowed to detect very recent observation allowed to detect circumplanetary material. So not the protoplanetary disk, but circumplanetary material, essentially material, the dust around the protoplanet. And this is quite impressive. So this is one clear case where we know that these dust cavities are the product of planetary disk interaction. In terms of the indirect methods, so the first case I want to discuss is the perturbation of the gas surface density. We know that the planet induce a gap, open a gap in the gas surface density, and the properties of the gap, like the width and the depth of the gap, are proportional to the mass of the planet, but also to the properties of the disk, mainly essentially in particular scale height. And we can observe this by looking at, for example, the CO profile, as shown in this work by Stefano Facchini. And this is what we did. This is again HD 169142. The continuum look like this beautiful double ring structure. But when we look at the gas, no, it's not that easy to find to actually visualize the gas gaps and rings. But with the help of multiple isotopologues, in this case is the 13CO and the C18O, we do recognize the double ring structure. This is interesting because the 13CO, this is the 2-to-1 line, which is optically thick. The emission peaks to the center. And this is consistent because in optically thick lines follow the temperature profile. So it's brighter where the temperature is high. The C18O transition instead, which is optically thinner, it is more sensitive to the actual gas surface density, and indeed it peaks to in the outer region. So this is a clear detection of gas rings and gaps. This is essentially the same story. Just I'm showing here the radial profile. We've seen the continuum as the two main rings, and the C18O does a sort of steps. This is because of lack of resolution in the line observation. You see the beam smearing, but it is clear that the gas surface density is reduced in correspondence of the dust gaps. Different authors also made use of dynamical simulation to make sense of the ALMA observations. And in this particular case of 169142, I'm showing here the simulations made by Claudia Tocci using the Phantom SPH code. And essentially, we injected two massive to Jupiter mass planets, essentially one inside the cavity and one in the gap between the two rings. And the observations and the simulations are essentially in pretty good agreement with the observations. We see the dust form two main rings, while the gas surface density is reduced by the first planet at 50 AU, more or less, 40 AU. And then when you move inwards and inside the inner dust cavity, the internal planet, the second planet essentially accretes all the material and essentially depletes the inner disk. Also in this case, we have a candidate planet, protoplanet at 40 AU. This was observed again in the near infrared. Was seen already in an image by Adriana Paul, and then was be analyzed by Gratton. And this is this point circle D has to be confirmed. But it's interesting because it is exactly where it has to be, in the center of the gap. Now the question is, okay, we know now we are quite confident that some of the gaps and cavities are produced by planets. The question is whether all gaps essentially host a planet. And for this, I want to talk a little bit about AS209. Allow me the citation because this is really the Lord of the Rings. It's a beautiful young disk. Is in Ophiuchus, and we observe this at moderate resolution for the exact reason to resolve the disk not only in the continuum but also in the gas. And again, we see a drop in the C18O brightness profile, which is indicative of a drop in the gas surface density. And the same disk observed at a higher resolution by the D-sharp team shows really many rings. This is why it's the Lord of Rings. Now we modeled this object using again Fargo, again other dynamical simulations. This time with Fargo, and putting one single planet at 100 AU. And the simulations essentially are consistent to the observation, according to the simulations, to the other simulations. single planet of more or less Saturn mass planet. First of all, it's able to produce the two narrow rings observed in the outer side part of the disk. But very interestingly, it also produces many other rings inside 50U. Now, this is very interesting because first of all, is consistent with a theoretical paper by Robin Dong, who was published a year before, and also Zhang et al. Using the D-sharp high resolution observations. Essentially, they came to the same conclusion that one single planet at 100 AU is able to produce multiple narrow rings and gaps. Now, I want to talk a little bit about spirals because if you remember, I said that GI, gravitational stability, one product of a gravitational stable disk are spiral structures. Okay, we do see spirals with ALMA, and one of the most convincing case for gravitational stable disk is Elias 227. The spiral was detected in the continuum many years ago by Laura Perez. You see the image on the left. Was confirmed by the D-sharp survey, and very recently in this paper by Paneke, it's clear that the dynamics of the gas dynamics is highly perturbed, and this is what you expect to see in a gravitational stable disks. So far there is no planet or companion detected inside the disk. So this appears to be a pure gravitational stable disk, and this is a very interesting object. But spirals are not always the product of GI, gravitational stability. This is the case of HD 10453, with the spiral arms are detected both in the continuum and in the gas. Here's the 13CO moment 8 map. But in this case, we know that the spiral is actually induced by the interaction of the disk with the stellar companion. The companion is outside the disk, is the star that you see on the bottom left. So cohesion is important when interpreting the observation of a spiral. It's also very interesting to look here at that you see that the spirals seems to be different when observed in the continuum and in the gas. But this is a natural consequence of the vertical of the 3D structure of the disk. The spirals in the continuum come from the midplane, while what you see when we look at the gas, we look at a layer above the midplane. This is another spectacular case. B. O'Reilly is a beautiful spiral-rich disk. Spirals are observed with ALMA in the gas. This is, in this case, is 12CO. Is moment 0 map by Tang and collaborator. You see two beautiful arms. And when disk is observed in the near infrared, is amazing. It's really rich of spiral structures. The ALMA continuum instead is it looks like a ring with a large inner cavity, a cavity of essentially almost more than 100 AU, seen on the right. And very recently, Curie et al. Detected point point-like source and essentially where it has to be according to the spiral structure, and this is shown here by the green arrow. So this is a giant protoplanet candidate at 100 AU. And remember, this number is another giant planet at 100 AU, protoplanet at 100 AU. So in this case, the spiral structure seems to be produced by the interaction with the planet. Although we don't know if here is not clear. Is the planet that induced the spiral, or is the disk that is gravitationally unstable, and part of the spiral is collapsed into a planet? But it's a beautiful object because it shows the ring, the spiral, and the protoplanet. Another very peculiar object is HD 10546. This is another very big star. The central star is slightly more massive than the Sun. And we knew about spiral structures in this object by other observations. For example, on the left you see the HST images by Davide Fedele. They identified two main structures, structure 1 and 3, that we now know they are two large-scale spirals. Structure 2 here was not easily recognized. That this is the backside of the disk. We know this now thanks to sphere observations. Again, sphere observations also identified many spiral structure even in the inner 100 AU inside the disk. Now, when we look at this object with ALMA, the continuum is very peculiar because it has an inner ring centered at nearly 30 AU with an inner cavity of more or less 20 AU. And this inner ring is extremely bright. And then a huge, very wide gap, more or less goes from 50 to 150 AU. And beyond this gap, there's this narrow, well, not so narrow, there's this weak ring, slightly eccentric. And there are also in this case that there are hints that the C18O is partially reduced. The abundance of C18O, again, this is a hint. This is evidence of a gas surface density perturbation, and we modeled this using hydro simulations, and we knew that there are hints by many observations that there should be at least two giant planets. So our simulations seems to agree with the presence of two giant planets, one inside the cavity and one in the gap. But this has to be confirmed. So again, we see the spirals, we see the rings, and the protoplanets candidates. So in this case, the spiral again is not clear if it's the product of gravitational instability or is interaction with the protoplanets. But ALMA is not only beautiful images of rings. We learn quite a lot also in terms of the global disk properties. For example, the plot here shows the evolution of the dust in different star-forming region. So one very important result to me is the appearance of rings in very young systems. So we knew already that young objects in Ophiuchus, a very young region, we have rings. But there are these three cases, Elias 24, GY91, and IRS 43, which are classified as class 1 objects. So from an evolutionary point of view, these are very young objects, younger than the one we saw before. And we did not expect, for ALMA, we did not expect to see evidence of planet formation at this very young age. But the fact that there are hints of rings and gaps in such young systems essentially implies that planet formation must start on a very short time scale. And that point is important, is relevant to the question when planet formation occurred. We have also hopefully evidence of growing disk. This result, this ALMA confirmed this result was partially known before. This plot here shows the distribution of the millimeter spectral index for disks in different regions, and the spectral index essentially the fact that the spectral index, the mean spectral index is so low, is around 2 point something, 2.2. It tells us that disks. This is a global spectral index. This is not spatially resolved, but is telling us that grains in disks are grown in size. Okay, there are grains larger than millimeter particles. So this means that this grain grow, and this is in good agreement with the core accretion scenario. On the other hand, when we look at another global property of disk, which is the total dust mass, is this nice analysis that show the distribution, essentially how it compares the mass of the exoplanets, as we know, with the current available mass of solids in disks at different ages. And what you see here is that class 2 disks on average seems to have not enough mass in solids to explain the population of exoplanets. On the other hand, younger disks, or again class 1 or even class 0, seems to have enough mass to form essentially to give rise to the exoplanet populations. So again, this is a hint that planet formation maybe start very early on, before the class 2 phases. Along the same line, also for the gas, I said that ALMA allows now to do complete survey of also in the gas. But we know, for example, for disks in the low pulsar forming region, but also other forming region, that essentially CO appears to be less abundant than what we expected, especially the gas to dust ratio measured with using CO is below the standard value, the 100 value, dust to gas of 1%. So this means that so something happened to CO. The question is whether this is a physical evolution, that is whether there is low CO mass in disks already at an age of the low pulsar forming region, which is between 1 and 3 million years, or it might be a chemical effect. In this perspective, there are ongoing ALMA services. In particular, it's important to think is the H-Pro ALMA large program that will study the evolution of the gas mass using CO and H+. So there's so far we can only say there is a hint that there's too few that the gas mass reservoir is reduced in class 2 disks, again indicating that planet formation must start early on. But future ALMA observations will for sure answer these questions. So to summarize all this story, so remember that the question was how and when planet formation happen in disks. I think that the properties of the fact that we see the rings in class 1 disks and the mass budget stories, which is the fact that there is not enough mass in solids and the missing CO flux implies this results imply an early start of the planet formation, so earlier than the class 1 phases, the class 2 phases. Sorry. The global properties of the dust, like the spectral index, but also the optical depth of the dust in the continuum in the rings, narrow rings, instead tell us that there is grain growth and there is also planetesimal formation in rings, and these findings are in pretty good agreement with the core accretion scenario, with the particular, and also with the streaming instability one. On the other hand, the evidence of spiral structure in some disks and the detection of giant protoplanets at very wide orbits. You remember I talked about at least 3 objects with a protoplanet candidate at 100 AU. These are difficult to reconcile with core accretion and are very much in agreement with gravitational instability. So to answer the question, how planet formation up in this, I think I can only reply with a question mark. It looks like there might be more than one actor in the story, and so there is evidence of a bimodal planet formation. Again, ALMA in the future will for sure help us. We first need to have a direct confirmation of the presence of this giant protoplanets and very wide orbit. And more importantly, but also important, is the observation of the gas and the molecular abundances in disks. So that's all from my side, and if you have a question, please go ahead. Thank you.
Thank you very much, Davide, for this very fascinating and inspiring talk. But before going to the questions and to give people a bit of time to type up their questions in the YouTube chat, I'd like to highlight a number of upcoming events organized by the European ARC network. So the first one is going to be on Friday, May 20. An iTrain session is organized introducing the new ALMA document using ALMA archival data, a primer. And then on Wednesday, June 1st, there will be the next ALMA recounts of cosmic conundrums given by Nicholas Ribber, and this time addressing the question, what do comets tell us about the origin of Earth? So with that, we move now to the questions. I see we have already one. The question is, thank you for this talk. Do you see differences in grain sizes as a function of different stages of disks or radial trends?
So in terms of radial trends, there are hints. There's at least a paper by Marco Tazzari on a couple of objects. But also there's another one on 163296. in terms of age, that doesn't seem so. I mean, at least probably the age difference between the different clouds is so close. There is not a huge age difference, so we don't really see this. And this is also appears to be consistent with the fact that the narrow rings, the analysis in by Kestulemond show that the narrow rings seems to have always the same optical depth. So it seems that at some point grain growth doesn't proceed. So like the interpretation by Stamler that larger particles essentially are already incorporated so larger grains are already incorporated in larger bodies like planetesimals. So we don't see a trend with time essentially.
Right, then we have more questions. Thank you for this clear talk and for the lovely images. I was wondering what information we will be able to get from polarization observations.
So, there have been polarization observations and with detection of the nice detection of continuous polarization. And so we expected, so the dream was to see the orientation of the grains due to, for example, the magnetic field. But what the scenario that is emerging, the picture that is emerging from this observation is instead that the continuous polarization seems to be driven by self-scattering in disks. Essentially, is the emission that is leaving from the disk. The photons are scattered from the dust itself, which gives important information in terms of the grain sizes, again, the population of grains. So showing again, reinforcing again the result that there's grain growing disks. But so far, this is the main result of the polarization in disks. So I don't know if there are new for sure there are new campaigns. But so far, this is many different observation of different objects seems to indicate that self-scattering is responsible of dust polarization.
So you have shown that even in the Lord of the Rings, even one planet can form multiple rings.
Yeah.
So can it be that planet formation will then occur sequentially, so that one planet might create more rings and create better conditions for other planets to form? Yes,
this is ideal. I mean, you first need a process that piles up material in a specific location, like a ring. And when you have a ring, it's much easier to induce the formation of larger bodies. There are different kinds of instabilities that can occur when you have a ring, and then you have the streaming instability, or even a local gravitational instability, because essentially you have a sort of delta in terms of sigma dust over sigma gas. Essentially, you increase rapidly locally. You increase the surface density of solids, dust, over the surface density of gas, and this can induce also an instability. So it can be also sequential. On the other hand, you have to be careful, because a planet, when you have a planet and you start to interact with a disk, the planet starts also to migrate. So the migration is not necessarily constructive for the other rings, so it can be destructive. Okay, and the migration is sought to stop when the planet is massive enough that open a wide gap also in the gas. So to answer your question, yes, no. So you can induce a second generation, so to say, planet formation, but you can also migration can also destroy. Although even in the solar system, the grand tax scenario expected the migration of Jupiter and Saturn had some influence on the formation of for example, of Mars, reducing the dust mass locally, for example. So yeah.
Fantastic. If I can ask one, it's really fascinating. If I can ask one more question. So you say that the planet formation start very, very early when the disks are still very, there's a lot of dust available, gas rich. In class 0 object, for example, you have a very strong, presumably, outflow. Does this, so this does not influence at all what is happening
So
this plane?
no, I don't think so. Well, the problem with class 0, as far as I know, is that the disks are maybe still too small, too compact. I mean, you're still piling up a lot of material. So the outflow itself is not. I mean, it's not a problem because of. I mean, planet formation is occurring very deep in the disk. It's essentially just a high density somewhere. It's the midplane of the disk. So what is occurring in the upper layers of the disk is not really important in this case. Okay, but class 0. So I mean, I think the disk is still at least what the surveys of class 0 object show so far is that the disks are still too small. Okay, maybe you still don't have enough material. Okay, you have enough material in the system, which is made the envelope plus the disk. Okay, but the high density part, so the disk is still is not massive enough.
Okay, so we start with class 1.
This is my I mean, my point of view. I mean,
Not with it. No, but I see. We have used up now our questions. So, Davide, I would like to thank you very much for this wonderful talk. I would like to thank all the participants for being here and for asking questions. To wrap up, I'd like to remind everybody that if they have any questions about upcoming events, or if anybody is interested to make use of the support offered by the European Arc Network, please don't hesitate to open a help desk ticket or to contact your one of the nodes directly. So this is it for today. We look very much forward to seeing everybody the next time, and goodbye. Thank you.
Thank you very much. Bye-bye. Okay.